Friends, I want to talk today about the connection between spin and the collective behavior of particles, what is called a spin statistics connection. It's a connection which is well known, for which we don't have any clue as to what the physical reason behind the connection is. So it's a very important topic. I want to talk about it, mentioning various other people who have contributed to this research. One of them being our universal guru, E.C. George Sudarshan. Now, spin is a common property of matter, from fundamental particles to planets, things spin. But in quantum physics, spin of fundamental particles is quantized. It can take only values in units of the Planck's constant divided by 4 pi or h bar by 2 with this value, which is a very small amount of action. Now, particles like electron, proton, neutron, most of matter, common matter, they're all half integer spin particles. Their spin is h bar by 2. Whereas photons, Z boson, W boson, and so on, they have an integer spin, h cross. And the Higgs particle, for example, is a zero spin particle. So these are integer spin particles, there are half integer spin particles. There is only these two classes. There is nothing in between. Now, the spin statistics connection states that identical half-integer spin particles satisfy the Pauli exclusion principle and Fermi Dirac statistics, which permit no more than one particle per quantum state. Whereas identical integral spin particles satisfy the Bose-Einstein statistics, which permits any number of particles in each state. So already by 1926, this was formulated, the spin statistics connection, very clearly stated. Now, in this talk, I want to deal with the following questions. What is the physical reason that the spin of the particles determine their collective behavior? Why there are only two quantum classes of particles, bosons and fermions? Why only the aggregate spin matters in the classification? We will see why that is an important question. And then finally, can we prove the connection between spin and statistics, which already hints at there is no such a proof with reason available today. Now, I had written an article last year in the Physics News, S.N. Bose 125 centenary year issue. The reference is given here. A version is available also in the archive. Now, George Sudarshan and Jan Deck wrote a book called Pauli and the Spin Statistics Theorem a few years ago, in which they state, everyone knows the spin statistics theorem, but no one understands it. What is proved, whether truly or not, whether optimally or not, in an acceptable logical sequence or not, is that the existing theory is consistent with spin statistics relation. What is not demonstrated is the reason for the spin statistics relation. This lament is not new. A Feynman admitted the lack of an explanation in his lectures in physics. He says, why is it that particles with half-integral spin are Fermi particles whose amplitudes add with a minus sign, whereas particles with integer spin are Bose particles whose amplitudes add with a positive sign? We apologize for the fact that we cannot give you an elementary explanation. An explanation has been worked out by Pauli from complicated arguments of quantum field theory and relativity. He has shown that the two must necessarily go together. but we have not been able to find a way of reproducing his arguments on an elementary level. This probably means that we do not have a complete understanding of the fundamental principle involved. So there is no understanding why this is so. Pauli in 1925 was dealing with electronic structure of atoms with the aid of analysis of complex spectra. There he stated, there can never be two or more equivalent electrons in an atom. So that's a statement of the exclusion principle. These electrons, identical electrons, equivalent electrons, are defined to be electrons for which, in strong magnetic fields, the value of all quantum numbers is the same. If in an atom one electron occurs which has quantum numbers with these specific values, then this state is occupied. Therefore, no other electron can be in the same state. So the Pauli exclusion principle can be stated as there can never be two or more equivalent electrons in an atom. For example, in an orbital, you cannot have two electrons with the same spin direction. If the spin direction is reversed, the state is now different. They are not equivalent electrons, you can have two, at most two. Now, in 1925, 1924, there was no theory of the collective behavior of atoms, what is called quantum statistical mechanics. There was classical statistical mechanics, but the quantum theory of atoms, monatomic ideal gas, was not known. The pioneering paper was written by Einstein. I will come back to this later. But once the Pauli exclusion principle was stated in 1925, next year, Enrico Fermi dealt with this problem, quantization of the ideal monatomic gas. It's a quantum theory, quantum statistical mechanics of a collection of molecules. He said, it shall in the present work be assumed only the rule that was proposed for the first time by Pauli and proved by many spectroscopic facts that two equivalent elements can never exist in a system whose quantum numbers completely agree. The equation of state and internal energy of the ideal gas shall be deduced from this assumption. This is the beginning of what is called Fermi-Dirac statistics. Now in Dirac, in the same year, wrote a very, very important paper in which various aspects of quantum mechanics was dealt with. 4 or 5 fundamental aspects. One of them was the quantum theory of monatomic gases which obey the Pauli exclusion principle. And you will notice that this was communicated by R.H. Fowler in the Royal Society, who again used this again the next year itself to talk about stellar systems obeying Pauli exclusion principle, white dwarfs. Now in Dirac's paper, he noticed the following. He derived the law of distribution of the gas molecules, and he derived this formula with this +1 here. This is a distribution, and he stated this formula gives the distribution energy of the molecules which obey this Pauli exclusion principle. On the Einstein-Bose theory, the corresponding formula is a different formula. So Einstein had already worked out, based on Bose's paper on Planck spectrum, the theory of monatomic gases, but it had a completely different fundamental assumption. It had a different distribution. And the crucial difference between these two, the Bose-Einstein statistics and the Fermi-Dirac statistics, you can see in this sign of this +1, -1 here. Now let's look at Einstein's paper. Einstein published this paper following Bose's paper. He states, a quantum theory of the monatomic ideal gas free of arbitrary prescriptions did not exist before now. This defect will be filled here on the basis of a new analysis developed by Bose. which this author has described as the most remarkable derivation of the Planck radiation formula. What did Bose do? You all know this, but let me briefly state it. He just said photons are particles, they are quanta. Photons are not electromagnetic waves. Hence, using waves in a box picture to calculate the Planck backbody spectrum is inconsistent. So what he was saying was, he wanted to derive the Planck radiation law, which is spectral density as a function of frequency, even by this particular formula, which is derived by Planck in 1900. It has these three factors. The total spectral energy is given by 8 pi nu square by c cube, which is a number of states. There is an average energy h nu, and then there's a probability factor exponential h nu by kt minus 1. So spectral energy is a product of all these factors. But the 8 pi nu square by c cube factor is derived in all derivations before Bose's dealing with this issue, was to count the number of standing waves inside a box, like a furnace. And that number is what is derived here as 8 pi nu square by c cube. But he says there are no waves. Photons are particles. That Einstein said photons are particles which obey the law E is equal to h nu, P equals to h by lambda. Why are you, why should one talk about waves at all? So that's what Bose wrote to Einstein when he sent his paper to Einstein. He said, I have ventured to send you the accompanying article for your perusal and opinion. I'm anxious to know what you think of it. You will see that I have tried to direct the coefficient 8 pi nu square by c cube in Planck's law, independent of classical electrodynamics, only by assuming that ultimate elementary regions of phase space has a content h cube. So what he did was the following. He assumed that the phase space is the PQ space is the shell, elementary shell if you take, with the radius P and delta P width, and use the fundamental quantum relations. Then he could write 4 pi p square dp as 4 pi this factor. This multiplied by the volume will be the volume in phase space for that shell. So now, since he assumed that the elementary region is a volume h cube, just by dividing by h cube, you know the total number of states available, which is this factor. This just multiplied by the two polarizations or spin directions of photons possible. You already get the 8 pi nu square by c cube. It's a very, very simple derivation, very straightforward, no mention of electromagnetic waves and so on. That was Bose's great advance. The rest of the factors, how to derive those identical particles and so on, these were already known. Even from Willard Gibbs solving the Gibbs paradox, already the identical nature of particles in statistical mechanics was already used in derivations. Now, so let's briefly look at what happened. Bose derived the Planck spectrum, assuming that photons is just a gas of particles, no mention of waves. And any number can be in a single state. They are indistinguishable and all that. Einstein took this idea very seriously and said, if a gas of quanta obey a distribution law, the same law should be applicable to atoms as well, except that the only difference, when you go to zero temperature, photons just disappear. There are no more photons. Whereas atom number is conserved, there's a chemical potential, and you get a slightly different formula. Instead of exponential energy by kT, you also have a constant. But otherwise, the distribution law is exactly the same. And from which Einstein, of course, predicted the phenomenon of condensation above a critical density. The lowest energy states can be occupied by a large fraction of particles. That happens well above the absolute zero temperatures, a new phenomenon. As you know, this was a very important prediction starting from Bose's paper. Now in all this, if you notice, particle need not be an elementary particle. The total spin of the aggregate of the particle determines this behavior, whether it's a Bose particle or a Fermi particle. For example, superfluid helium is an example of this condensation. It has 2 protons, 2 neutrons, and 2 electrons, but spin equal to 0. All fermions, but the aggregate is as a boson. Superconductivity, 2 paired electrons are responsible for conduction without resistance. Bose-Einstein condensation of rubidium atoms in the magnetic trap, which happened in 1995, 37 protons and 37 electrons and 50 neutrons, a giant aggregate of fermions, 125 particles, but the total spin can be 2 or 1 depending on the electron spin direction, and you get a Bose-Einstein condensation in the system. So they behave definitely as bosons. This is Saptarshi already mentioned about this. The BEC which we produced in TIFR in a crossed optical trap. It's another, same again in rubidium. This was our offering to Bose's memory. That was a primary reason why we did it at that time, though we continued with some studies for a few years after that. Now there is also another Indian connection in this collective behavior of particle. Chandrasekhar in 1931, following Fowler's work on white dwarfs, he found out that if you increase the mass of the white dwarfs beyond a certain limit, what is called Chandrasekhar limit now, they will collapse. They will, even the fermionic behavior cannot stop gravity from collapsing a star if a critical mass is exceeded. So there are so many examples where collective behavior of particles just fall in 2 classes, and all that depends on just the value of the spin. Most spectacular example is this more recent work on the the laser cooling of lithium atoms. Lithium-7, it has total 10 fermions, so it is a boson, even number of fermions. The collective spin is an integer spin boson, which Bose condensates, and it can be compressed to very, very small spatial regions. Whereas lithium-6, it has 9 fermions total, and therefore it's a fermion, aggregate is a fermion, and you can see, even though the temperature is being reduced, the atoms refuse to go to a small volume. The Fermi pressure is acting. So the social distancing behavior of particles partition them into just 2 classes, bosons and fermions. The particles can be aggregates of fundamental particles. And all this depends only on spin. That's the most interesting fact. Now, the variety of this myriad phenomena depend only on the spin of the particle is a very, very fundamental feature, which is what we want to explore now. There's a picture of Pauli and Niels Bohr looking at a spinning top. Pauli said in his Nobel lecture of 1945, in order to prepare for the discussion of more fundamental questions, we want to stress here a new law, a law of nature, which is generally valid, namely the connection between spin and symmetry class. A half-integer value of the spin quantum number is always connected with antisymmetrical states, exclusion principle, and an integer spin with a symmetrical state. This law holds not only for protons and neutrons, but also for electrons. Moreover, it can easily be seen that it holds for compound systems if it holds for all of its constituents. If we search for a theoretical explanation for this law, we must pass to the discussion of relativistic quantum mechanics. Since we saw that it can certainly not be explained by non-relativistic mechanics. It's a very surprising statement because we already saw the manifestation of this law in a very happens in a and very non-relativistic situation like laser-cooled atoms, almost zero kinetic energy, and so on. So Pauli found that he couldn't find an explanation within non-relativistic mechanics. The question is whether he found the explanation in relativistic mechanics that we will explore now. Now, a description of these two classes is very easy in quantum mechanics. Even though we don't know the reason, the description is very easy. Let's look at it. Okay, let's say we want to write down the wave function of two particles, psi1, psi2, and there's a product of those wave functions as a joint wave function. Of course, if you write it just as a product, there's no difference between boson and Fermi. So that we cannot do. We want a difference. And this is what Pauli mentions as symmetry class here. For an integer spin, we write a symmetrical wave function. If you exchange these two particles, the relative phase between these two product and the exchange product is plus. For fermions, we put a minus sign here. So it's a anti-symmetrical kind of a wave function, total wave function. So integer spin is associated with symmetrical states, and half integer spin is associated with anti-symmetrical state. If you do this, then so exchange. That's what I want to show there. If you do this, the Pauli exclusion is almost it's automatically implemented, because if you put x1 is equal to x2, if they are brought together into the same state, so these are the state labels. If they are brought into the same state, x1 is equal to x2 kind of thing, then both these two terms, they become equal, and the difference will go to 0. Whereas here it becomes twice the total wave function. If you take the square of that 4 times, so the enhanced probability of the same condensation and so on comes from that property. So stated in a graphical way, you can start with the two initial states, and there's a process to final states. There's a direct process, and there's a process exchange process in which the coordinates and all the quantum numbers are interchanged. So these two processes give identical final states starting from identical initial state, but they're indistinguishable. By looking at the final states and the initial states, we cannot distinguish these two processes. We can also look at it as a scattering process, where two particles come together and scatter. The same process can happen through another mode, which is scattering like this. So one is scattering through a small angle, another is scattering through a large angle different by pi, but the final and initial states are exactly the same. They are indistinguishable. So that is what we had to calculate, because what we do in physics today is that for the Bose particles, we add these two amplitudes with a plus sign. This is what Feynman was referring to. For Bose particle, we put a plus sign because that's what gives a correct answer for what we know from experiments. And for Fermi particles, we put a minus sign arbitrarily, and therefore then we can get the Pauli exclusion from the wave functions. Pauli obsessively took it on himself to prove with reasons the connection between spin and statistics. But what he managed was just a mixture of reasons. Nobody thinks that is a proof in the sense of a physical reason. So this is a paper by Pauli in 1940, the connection between spin and statistics. He says, in the following paper, we conclude for the relativistically invariant wave equation for a free particle, non-interacting particle, from postulate 1, according to which energy must be positive, necessity of Fermi-Dirac statistics for particles with arbitrary half-integer spin. From postulate 2, according to which the observables on different space-time points with a space-like distance must be commutable. That is, measurement on one point should not affect the measurement on another point. The necessity of Bose-Einstein-Bose statistics for particles with arbitrary integral spin. Now, see what is happening. What he tries to prove is the following. If identical particles with half-integral spin were to follow bosonic behavior, then the positivity of energy will be violated. If identical particles with integer spin were to exclude each other to show fermionic behavior, then a measurement at one point can affect the observable at another point instantaneously. So these are entirely different reasons for the bosonic and fermionic behavior. There's no common reason connected with the value of the spin which he is able to find. I want to illustrate for people who are really interested in the formalism, just one point about the Fermi particles. I don't want to go into details of this. This can be found in the book by Sudarshan and Ian Deck. But let me just indicate what is happening, the kind of proofs which Fermi and others, Pauli and others did. If you look at the Dirac equation, you know that the solution, zero momentum solution, you have the positive energy and the negative energy solution. You have a general superposition possible as the general wave function. And if you calculate the energy by operating with del by del t, you get an expression S star A minus B. So there is a minus which comes because of this positive and negative energy solutions. Now, when you go to field theory, these coefficients A, B, and so on, they become operators. They become creation and annihilation operators in analogy with optics. If they obey bosonic commutation relation, suppose A dagger, etc., obey bosonic commutation relation, like commutator is 1, all other commutators are 0. Therefore, similarly for the creation and annihilation operator for the positrons or the anti-electrons, obey the similar commutation. Suppose it is commutation relation. Then when you calculate energy, you get this kind of an expression, A dagger A minus B dagger. It's similar to this. But B dagger can be written in terms of the B dagger B. These are the number operators, A dagger A and B dagger B. So what you end up with is M or MC square multiplied by number of electrons minus number of positrons. And these numbers can be arbitrary. So this can be negative or positive, arbitrary. You know, it can be anything from minus infinity to positive infinity. So the positivity of energy is violated if bosonic commutation rules are applied to spin half particles. That's what it shows. On the other hand, if they obey, if these operators obey anti-commutation, a dagger anti-commutator, which means there's a plus sign here. Suppose these are the laws which are obeyed by these operators, then when you calculate this quantity, obviously you get plus here. Then the energy is positive. It's a sum of the number of electrons and number of protons. So this is what Pauli was indicating. And if they, in fact, this is the only way to do the theory of Dirac spinets, because if the Pauli exclusion has to be obeyed, you need the fermionic anti-commutation, because then if you look at the anti-commutator for A dagger and A dagger, or A and A operated twice, it is 0 because the anti-commutator is 0. Therefore, you get this expression. If vacuum state is operated twice by the same operator, you get always a 0, which means A dagger operating on the state 1 is 0. So that is Pauli exclusion. You have already, if there is an electron there, when you operate one more with the creation operator, you get a 0. So this is a just summary of how these proofs go. But I don't want to go into details of that. The essential point is, in relativistically invariant quantized field theories, the following conditions are expected to be fulfilled. Vacuum is the state of lowest energy and all energies are positive. measurements at two separated points cannot disturb each other, and the probabilities are always positive. What Pauli showed was that half integer spin, Dirac spinors, and Bose statistics, if they put together if these two things, then the positive energy postulate was to be violated. For integer spin and Fermi Dirac statistics, postulate 2 will be violated. So that therefore these proofs are no-go proofs. Since these reasonable assumptions will be violated, that should not happen in nature, is what Pauli was trying to say. But it's important to note that the reasons are entirely different in the two cases. Bosonic behavior is linked to validity of locality, and the fermionic behavior is linked to existence of a lowest energy state and positivity of energy. There's no common reason. So if you look at the whole, various people have worked on it, but if you look at the whole set of proofs, one can notice the following. The logic and steps in the proof for the fermionic spin half fields are not applicable to bosonic spin zero fields and higher spin, integer spin. The proof for the integer spin particle follow an entirely different reasoning based on the causal independence of the field operators at specially separated points. This fact means that the physical reason for the spin statistics relation is not part of the proofs. If it were, the steps would have been similar to a large extent. Further, the proof for spin half particles depend on the postulated anti-commutativity of the fields. However, notice if the choice of commutator versus anti-commutator is just the same statement as a classification into bosons and fermion, then the proof is terribly circular. We do not know why spin half fields should obey anti-commutator because there is no classical analog, apart from the only fact that we need consistency of the theory. Now, what is most important from my point of view is this: two fermions, electrons, protons, etc., together is also just a pair of spinors, same Dirac field, but they behave as a boson, superconductivity, BC of atoms, etc. So this single crucial fact kills the logic in Pauli's proof and its refined versions, because the field has not changed to another kind of a integer spin field. The same spinor fields, but they behave as bosons. So what could be an acceptable proof for the spin statistics connection? Because it is there in, it's one of the most important fact about nature, applicable in atomic physics, optics, and in nuclear physics, everywhere. The proof should have a sound physical basis, certainly, a reason for the connection. The reason should be the same, at least similar, for both classes of particles. The reason should be physically linked to the property of spin angular momentum. Of course, it is called, otherwise there's no point calling it spin statistics connection. The proof should make sense for just two particles as well as for an arbitrary collection of identical particles. Then the proof should be clear why the general law applies universally to all particles as well as their aggregates, relativistic or non-relativistic, interacting or otherwise, without any exceptions. Because people have looked at experimental evidence for even a tiny violation, nothing has been found. And Pauli was very aware of this, limitations of what he was doing. So he ended his Nobel lecture thus: at the end of this lecture, I may express my critical opinion that a correct theory should neither lead to infinite zero-point energies nor to infinite zero charges, that should not use mathematical tricks to subtract infinities or singularities, nor should invent a hypothetical world which is only a mathematical fiction before it is able to formulate the correct interpretation of the actual world of physics. Of course, we do all this in our theories today, but this is a veteran saying what he thinks. From the point of view of logic, my report on exclusion principle and the quantum mechanics has no conclusion. That's what Pauli says. He ends with that kind of a statement. And as we saw earlier, in this book, Sudarshan and Duck said something very similar. The point is, we are not able to find the physical reason behind this ubiquitous law of nature, in spite of our search for nearly a century. Nearly a century. And particles keep spinning without telling us, giving us a clue. So I want to look at the proof of spin statistics theorem, the rest of the talk. I want to mention something about magnetic fields because that's very important in this. If you look at a charged particle, there is electric field. And if you take a magnet or a coil of current, there is magnetic field. But magnetic field is it's linked to motion of electric charges. It's a transient. If there is a charge moving, there is magnetic field. If the motion stops, there is no magnetic field. So charges and currents are the fundamental quantities. What we call magnetic field is essentially a current, but linked to a distance, spatial distance. Therefore, we call it a field. Now we know that parallel currents attract and opposite currents repel, and the magnetic field properties are described. These are all described in terms of properties of the magnetic field. And we also know that if there's a magnetic moment, a tiny magnet in a magnetic field, there's a torque or a interaction energy equal to mu dot B. All this is very familiar to all of us. The magnetic moment of a magnet, as well as a fundamental particle, ultimately is a closed current of the charge of electricity. It's something which is going around and repeating. Hence, every phenomenon that depends on the magnetic moment involves an interaction with another current or a magnetic field. That's inevitable. It's a current-current interaction. The magnetic moment is defined as R cross the current. And the current is electric charge density multiplied by the velocity. It's just a bilinear in the two. What exactly is a spin? Spin is a very similar quantity. Spin is defined as R cross J integrated. Of course, there's a factor of 2 differences there in the definition. But now the current in the case of spin is a mass energy density multiplied by the velocity. It's very similar. Here it is electric charge density, here it is mass energy density. And that is a real clue, because what is mass energy density? Spin is a closed current of the charge of gravity, because mass and energy is a charge of gravity, is a source of gravity. So what is magnetic moment to electromagnetism is spin to gravity. Hence, every phenomenon that depends exclusively on the spin moment should involve a gravitational interaction with another current of matter. That is a very straightforward physical expectation. So gravity is a clue. But now, if you look at the phenomenon of gravity and its relation to spin, we know standard gravity, attractive gravity that we know, but that doesn't act on spin in any exclusive, in a particular way. All particles with spin or without spin just fall the same way. So we have to have an analog of magnetism in gravity. That's the only way we can have a current-current interaction or a spin-spin interaction. So is it the case that the spinning Earth has, other than the attractive gravitational field, there is also a magnetic-like gravitational field? It turns out to be true from general relativity. It's not part of Newtonian physics. It's a part of relativistic gravity. So let me just introduce that concept. We don't need any details. If you look at relativistic gravity, just a relativistic theory of gravitation, which is general relativity, if you take 2 currents of masses, These are just masses which are moving. So the two currents, parallel currents, what is the result? The ripple that is known from relativity. Or if you have two spinning celestial objects, it is known that there is an attractive force between them. That's a current here and the current here interact, and there is a force between them. This is called gravito-magnetism. General theory of relativity predicts this. The experiments show very good evidence for it, but it's extremely tiny field. It's very small because of 1 by c square kind of a diminishing factor. So if you look at the real gravitational field near Earth, there are the familiar Newtonian field, attractive field, plus a magnetic-like field. It has the same dipole pattern on this rotating Earth. And if you look at its value at the surface of the Earth, you can see that it is proportional to the angular velocity as expected, because the current is what matters, but diminished by this factor gm by c square r. Gm by r is the potential, and that divided by c square. So it's a very tiny effect, tiny field of just 10 minus 14 radian per second. Very difficult to detect, but it has been detected by various means. One experiment is with gravity probe B. One can look at it separately. Stanford University website has some details. So these things are known from relativistic gravitational theory, that there is magnetic-like gravitation as well. So I repeat this: mass and energy are the sources of gravity, and spin is a closed current of gravity's charge. Therefore, physical phenomena that exclusively depend on spin must be linked to gravity. What I'm saying is, gravity must be the clue behind the spin statistics connection. But then people would say gravito-magnetic fields are just too small to affect anything in terrestrial physics. Then how can we even think of bringing those fields in such widespread phenomena as Pauli exclusion or other Bose-Einstein condensation and so on? The question is, are they really too small? Let's look at, let's calculate. If you look at the gravitational potential in our roofs, we can calculate the gravitational potential due to Earth, gm by r. You get a number. It's about 10 to the 8 meters square plus by second square. But if you calculate the potential of the sun in our rooms, it's actually 10 times higher, not smaller. Gravitational field from the Earth is from the sun is smaller, much smaller than the gravitational field, gravitational pull from the Earth, but the gravitational potential is actually 10 times larger. So if you look at the gravitational potential of the Earth, Sun, galaxy, etc., you will see that the larger structures or the distant masses dominate. Galaxy is 1,000 times gravitational potential. So we can calculate the gravitational potential due to all the matter in this universe. That is a calculable number. We can take a shell like any shell at a distance r with a thickness dr, 4 pi r square dr multiplied by gravitational constant and the density divided by r for the potential, integrate up to the Hubble radius, and you get a number. It is 10 to the 17 meters square per second square. It's a billion times more than the Earth's gravitational potential. Earth's gravitational potential is only 10 to the 8 meters square per second square. Now, this 10 to the 17 meters square per second square is a very interesting number because it's also equal to the square of the velocity of light. I don't want to go into details now, except to say that instead of the Lorentz factor is 1 minus v square by c square, if I say it is 1 minus v square by potential of the universe, all experimental result will agree with this proposal that relativity is based on gravity of the universe. See, once we see these numbers, we can notice immediately a serious problem with the foundations of fundamental theories. Universe with all its matter content and gravity existed ages before we started making our theories. Just that we did not know about this until 1930. All our fundamental theories of the physical world were completed well before we acquired any significant knowledge about the physical universe. So we didn't know about this. So therefore, our theories of relativity and dynamics, as well as theory of gravity, were all developed explicitly assuming empty universe, no matter, no significant amount of matter. So, however, the gravitational potential of matter is as we just saw, it's a billion times larger than our local potentials. And if these were to have any say in dynamics or relativity, then we have completely missed out all this in our theories. All our experimental tests, in contrast, are in the unavoidable presence of cosmic gravity that we cannot avoid. It's always there. So it's a very funny situation. Empirical evidence includes all cosmic gravitational effects if it is there, whereas fundamental theories as constructed do not, because they were completed before we knew anything about this matter. So our most believed theories are either incorrect or very incomplete, one of the two. Remember our successful planetary models. They were successful with the Earth as a center. So it's a history repeating. See, if you look at the whole universe of matter, there's only one frame, special frame, in which every matter is at rest. And the cosmic background is isotropic and all that. If you move in this universe, even with a small velocity, all the matter in the universe is relatively moving. There's a current of matter, and the space is anisotropic. Okay, so this is so in every moving frame, in the rest frame of everybody who moves in this real universe, there's a large current of matter. All matter in the universe, it generates a large current. So if you look at a particle which is going in a circular orbit or something, like electrons in a magnetic field, in this large potential, gravitational potential of the universe, what we really, in the frame of the particle, what we see is this, right? There's a very large curl of the current of matter. There's a circular current of matter. We can calculate the vector potential, gravitational vector potential. It is just the gravitational potential multiplied by V by C, like in electromagnetism. And the curl of that is a gravito-magnetic field. And you get an expression for that. So we can calculate this. Since the matter is very large in amount, this also is expected to be very large. Let's see how large it is. If there is a gravito-magnetic field, it will apply a deflecting force on any piece of matter moving through that, right? Just like electromagnetism, there is a magnetic field, there's a charged particle moving through it, it will get deflected. Exactly the same thing will happen for a stone which is thrown in a rotating frame because of the large gravito-magnetic field generated by this huge current of matter. And this is the expression, I'm just calculating this expression. The force is proportional to mass, the velocity, with the V cross B force, right? Just that. But this factor is 1 actually. Now, so what you expect is a deflection of such particles, and this factor is 1, and you can see immediately this is a Coriolis force. The Coriolis force is a genuine gravitational force because of the matter in the universe. But that is not our topic today. All this has been written up in, you can look at this particular reference, A New Gravitational Paradigm for Relativity and Dynamics, which I call Cosmic Relativity, in which it is established that dynamics and relativistic effects in motion are completely determined by the gravity of the matter and energy in this vast universe. Matter-filled universe is the determining master frame for dynamics and relativity. Now, back to our proof. Just to tell you that this is the case, I want to give very briefly 2 proofs. forget about gravity. Just imagine that atoms are slightly charged, 1 part in 10 to the 35. So you won't see it in the laboratory, any effect. But when Maxwell was developing his theory, we didn't know anything about the matter in the universe. So the matter was there, but we didn't know. But because of a slight asymmetry of charges in the atom, because of the vast amount of this matter, there will be a very, very large electric potential all over the laboratory, right? That's what is expected. So Maxwell equation and Lorentz force would have worked only in inertial frames. If you go to an accelerated charges frame or a rotating frame, new mysterious forces proportional to the electric charge would appear because this large gravitational potential, electric potential, because of this slightly charged matter all over the universe. And we would conclude that there were pseudo electromagnetic forces over and above real electromagnetic forces which we generate in the laboratory with coils and voltages and so on. We were saved from this embarrassment because atoms are very, very neutral electrically. That's the reason for this. Otherwise, all this would have been, there would have been a electric Coriolis force, electric centrifugal force and all that. It is not there because atoms are truly neutral. But matter is not neutral gravitationally. All matter has gravitational charge, mass and energy. Universe is gravitationally very charged. This alone tells us very plainly that the pseudo forces we see are in fact gravitational forces. Now very important. I want to pose a puzzle for which there is no answer in today's physics. It's an extremely simple problem. I presented it to various atomic physicists and condensed matter physicists in the country. There is no answer because nobody has given me an answer. Just look at a charged particle in a uniform magnetic field. So there is a cyclotron orbit, E by m. That we all know. Now look at the ground state of that in quantum mechanics. In quantum mechanics, just having a frequency is not enough. It has to obey the Bohr-Sommerfeld condition. The orbit has to close on itself and the total phase of the wave function should be 2 pi times an integer. That condition has to be valid. That's a quantum condition. So if you calculate, you can calculate E dot dl integrated over the orbit. If you calculate, you get 2n pi. And this is why we say flux is quantized. That is, the orbit is such that the magnetic flux enclosed by the orbit is always a integer times h by e. This is called flux condensation. That means orbit is quantized. However, the electron has a spin. This calculation we did without considering the spin. If you calculate with the spin, what happened? There is an extra phase coming from mu dot b interaction. It's a magnetic field. So we have to recalculate this phase. What is a phase of one cyclotron orbit of a single electron in a uniform magnetic field? There's a simple quick answer. We know that the cyclotron phase of 2 electrons in a superconductor with s equal to 0 or s equal to 1, because there are 2 electrons, is 2 pi. Because there is flux quantization obeying, it is obeyed perfectly in superconductors. Therefore, if it is just 1 electron, it has to be pi. If it is pi, then the orbit will not close. We cannot have it, but let's calculate it explicitly. We can calculate mu dot b in the orbit. Its energy is mu dot b, and the orbital duration dt is 1 divided by the frequency of the orbit. So if you calculate just a straightforward calculation, you can verify that it is pi and not 2 pi. So it's a devastating result. It's a devastating result because the quantum phase in a simple situation of an electron with an half-integer spin in a cyclotron motion in a magnetic field does not obey a basic law of quantum mechanics. There's no answer in today's physics, let me assure you. So unless there is more phase coming from somewhere, from another interaction involving the same spin, and that is gravity. interaction energy of a spin in a gravitomagnetic field is S dot B, like mu dot B, but now with a factor of 2 because we saw that there's a difference in the definition of magnetic moment and spin, a factor of 2. So we can calculate this very straightforwardly from whatever we know already. We know what the magnetic field due to all the matter in the universe is that we calculated. It is 5 by c square, which is a factor of 1. Curl of V, which is 2 omega. So Bg here is 2 omega, where omega is a rotation velocity. So we can calculate this phase, quantum phase of an electron in a cyclotron orbit. What's the gravitational contribution coming from the matter in the universe? That also is another pi. So the pi from the electromagnetic magnetic moment, magnetic field interaction, and a pi from spin gravitomagnetic field interaction. It's totally is either 0 or 2 pi. So we are okay. So that is a solution. That is a solution to the fundamental puzzle of this phase of an electron in a uniform magnetic field. Cosmic gravity is a solution to this. So that's a proof. This is a real proof that cosmic gravity is real and important even in these elementary problems. So we have now a definite proof of the reality of the cosmic gravity and its importance for quantum dynamics through spin. So reason for the difference between bosons and fermions is clear. The answer should be in this gravitational interaction. Cosmic gravity and spin, it contributes to many effects in the paradigm which I mentioned, cosmic relativity, spin stasis connection, spintronics in chiral molecules, fractional quantum Hall effect, geometric phases in chiral transports. But today, our topic is spin stasis connection. So now let me prove this connection very simply. We saw that the scattering of two particles, one of the amplitude is this, and the other process is a direct exchange scattering. And the difference between these two, the only difference between these two, that one is through a small angle scattering, another is through a large angle, different from this scattering by angle of pi. This scattering is through theta, and then this scattering is through pi plus theta. That's the only difference. Let's calculate the phase. The mu dot B, the S dot B, gravitomagnetic field, and the spin interaction happens only here because this is where the angle changes, the momentum changes, there's a rotation. The particle which is going there rotates through a small angle, and that's the only time there will be a gravitomagnetic field interaction. So we can calculate this phase very straightforwardly. This is a picture. When the small angle scattering happens, there is rotation for a small amount of time, dt. We calculate that spin magnetic field, gravitomagnetic field energy, S dot B, multiplied by the time of interaction. You get omega t, which is just the angle. You get the expression 2s theta, the phase shift in this process. What's the phase shift in this process? That also can be calculated. It's also a similar expression, but now a different angle, theta 2. The difference between theta 1 and theta 2 is pi. So phase difference between these two processes, you get a very simple expression. It is just S times 2 pi. The spin value times 2 pi. That's a final phase difference between those two expressions. So exponential e to the this factor is a sign which should come between these two processes. Okay. So you can easily see that for a spin zero particle, of course, there is no interaction with the gravitomagnetic field of the universe. So the phase is e to the I0, which is 1, plus, whereas if it's a half integer spin, you get pi. So e to the plus or minus I pi is minus 1. So fermions, all fermions will have a minus sign as a relative phase between these two processes. All the integer spin particles will have a plus sign between these two processes. So we have found the reason as well as the proof for the spin statistic connection in a very simple way. Once we realize that cosmic gravity is important, and that is that's a real contributor to quantum phases even in simple situations. So we get an integer spin particles plus sign and the half integer spin particles minus sign. I have proved the spin statistic connection and found the physical reason, what Pauli had been searching for, what Sudarshan had been searching for, what many other people have been searching for, the physical reason as well as the proof for the spin statistic connection. It has to do with cosmic gravity. What about interacting particles? No problem, because the proof is general. The interaction phases are the same for both amplitudes. If you go back here, you can immediately see that interaction happens when the particles come together. The particles coming together is exactly the same. It's only the angle through which they scatter which is different. So therefore, the interacting particles, the proof is exactly the same. One need not assume that the particles are free. What about local gravitational fields in the environment, like the Earth's gravitational field and so on? That also should contribute. That's a very interesting question. The phase depends on the product of the interaction energy between the spin and the gravito-magnetic field, as well as the time of interaction. One increases with the gravitational potential, but the other decreases because of gravitational time dilation. So they cancel out actually. Therefore, spin statistic connection remains robust. It is not sensitive to small gravitational perturbation from local gravitational fields. So we come back to this, what this gentleman said. Pauli said, from the point of view of logic, my report on exclusion principle and quantum mechanics has no conclusion. So as I said, everybody knows the spin statistic connection, but no one understands it. The situation is now remedied. It is shown conclusively that the gravitational quantum phase of the spin of the particles, due to the interaction with the matter in the universe, is a real reason for the spin statistics connection. I supplemented this proof with another fundamental demonstration of the only solution to the phase puzzle in the simple problem of an electron in a magnetic field. This I use as a proof for showing that the cosmic gravity is a real effect. The universe is self-sustaining. It provides for both its variety and the stability. Variety because of atoms and so on have this variety because of Pauli exclusion. Stability, again, because these two classes have degeneracy, pressure and so on, you get a stability. And I end my talk here. Thank you. The references are here for this particular topic. Thank you very much.